Thomson and others' experiments to try to find electric charge were only somewhat successful, having got the charge to the right order of magnitude. In 1909, this graduate student of Robert Millikan, a young man by the name of Harvey Fletcher, solved the problem in an afternoon. Instead of using water, he decided to use a very fine oil, the kind used for watches. And he used an atomizer bottle, the kind used for perfume, to spray that oil. The beauty of the oil is it doesn't evaporate like water does. He then placed at the bottom of his chamber, or underneath the oil spray, a pair of metal plates that were separated by some distance d, and in the upper plate was drilled a number of small holes. The plates were connected to a battery so that an electric field could be applied, and then he used a microscope to observe the droplets. By adjusting the field between these plates, he could balance the weight of the droplet and so suspend it depending on the amount of charge on each droplet. The idea was simple, and it was no different from Thomson's idea. The idea was that the oil that was sprayed would pick up some charge, just like the water droplets would have. If the charge was only carried by the electron, then when the charge of the oil drop was measured, it would have to be some multiple of the electron charge. It was then only necessary to find the common denominator of the charge measured on all the drops over many experiments. So let's go through this Millikan oil drop experiment of Fletcher's bit by bit. As we said, the atomizer perfume sprayer sprays a fine mist of oil, and each of the tiny droplets should pick up some charge due to the friction of the atomizer. As they fall, they enter the space between the two charged plates. Fletcher adjusted the electric field between the plates until one of the drops he was watching would fall with a constant velocity. He found the mass of that drop from a measure of its diameter and because he knew the oil's density. Then, because he'd set the electric field strength, he was able to calculate the drop's charge. Let's see how the charge on the oil drop was actually determined. Remember that our oil drop is made to move with a constant velocity. That means that the acceleration on the oil drop is 0. And that there were two forces acting on the oil drop: its weight and a force due to an electric field. Using Newton's second law, we find that the net force is the difference between the electric force upward and the weight downward, Fe minus mg, and that has to be equal to 0. If we rearrange this, we get Q equals mg, and if we rearrange it again for Q, we get Q is equal to mg divided by E, the weight divided by the field strength. This seems simple, but Fletcher spent hours and hours and hours watching and measuring and then calculating the charge of a huge number of oil drops over many experiments. He even went on to add a correction for the viscosity of the oil drops in the air, which provided a further upward frictional force, and he did all of this without a computer or a calculator. As I said before, the experiment was repeated again and again with increasing accuracy and by many other groups until we arrived at the accepted value of the elementary charge on the electron, 1.602177 times 10 to the minus 19 coulombs. Here again, to help you get some sense of the historical experiment, is a picture of the setup used by Millikan and Fletcher to determine the charge on the electron. And as you can see, the whole thing fits on one lab bench.